Okay, so we've seen the Lagrangian description of motion, and in that context we looked at this basic example, this fundamental example really of rigid motion. And then we introduced the notion of the Eulerian description of motion. And you noted that I used for the first time perhaps my prop of the bottle with the fluid inside it, and we used the window to make the point that the Eulerian description of motion is natural for fluids. Okay? So that's where we're going to pick up. The Eulerian description of motion okay, and we will note here that it is natural for fluid mechanics. I should also remark that the fact that the Lagrangian description is natural for solid mechanics, while the Eulerian description is natural for fluid mechanics, does not preclude the description of fluid mechanics in a Lagrangian framework, nor the description of solid mechanics in an Eulerian framework. Okay? They can both be done. All right? It's just that one of them is natural for each type of material. Okay. What we will do now is look at the same example of rigid motion and write out the corresponding Eulerian velocity and acceleration. Okay, so we'll go back to our rigid motion. So recall rigid body motion. Okay, so same picture as before, basis. We have our body in the reference configuration, omega naught. We have put the position of a particle, capital X, and we are looking at a rigid motion. Okay, at least this motion is meant to be rigid, even though it may not look terribly rigid. Okay. And this is c of time plus q of time acting on x. Okay, that is our motion. Okay, just as before. Okay, now we're going to write out our Eulerian descriptions, but in order to construct them and really demonstrate that they are the same, we're going to actually start out with the Lagrangian description in each case and then go to the Eulerian description, okay, or the Eulerian formula, if you will. Okay, so let's consider the Lagrangian velocity first. Okay, which is v. Parameterized by x comma time equals now c dot plus q dot x. I'm going to dispense with the explicit indication of the time dependence of the vector c and the tensor q, okay, just to save some space here. All right, we have this. Now, we want to rewrite this as little v of x comma t. Okay, this is not at all difficult once we realize that phi of x comma time is actually little x itself, which for this rigid motion is c plus qx. We're going to use this relation to invert the description, right? We're going to invert the description of motion to write x equals little x minus c q inverse. Okay, I've just inverted the relation on the previous line, right? The equation on the previous line. But Q is orthogonal, right? But Q belongs to this special orthogonal group in 3 dimensions, SO3, right? Which implies that Q transpose Q is the second order isotropic tensor, which also means that Q inverse can actually be written as Q transpose. Okay? That's the special property of orthogonal tensors. All right? So, it implies for us then that capital X is Q transpose X minus C. We're going to use this relation and substitute it into our expression for the velocity, right? We're going to rewrite now V of little x comma time equals C dot plus Q dot. Now, before I finish that up, let's just go back one slide and recall what we had here. When we wrote things out in terms of the Lagrangian description of motion, right, we had this, right? And what we saw is that we had Q dot multiplying x, right? But now we're going to rewrite x. So we have Q dot acting on capital X, but that we're going to rewrite with the expression at the top of this slide, right? So we now have Q dot Q transpose X minus C. Okay? And straight away you note here we have reparameterized the same velocity, but now with the spatial position little x. Okay? Now, we're actually done here with writing out the Eulerian velocity, but we're going to do a little more work to make this more transparent and to connect back to something that you probably know from your earlier study of motion, right? Of your earlier study of rigid motion. In particular, what we're going to do is to focus our attention for about a minute on this quantity, Q dot Q transpose. Okay? In particular, we are going to note that we can rewrite this thing as follows, right? Let's start out with Q transpose, which, because Q belongs to SO3, is equal to the second order isotropic tensor, right? And this is because Q belongs to SO3, right? It's an orthogonal tensor in 3 dimensions. Okay. But what this now implies is that if you take the time derivative of this expression, we get Q dot Q transpose plus Q dot transpose, which is equal to, on the right hand side, 0, right? Because the second order isotropic tensor is constant. Okay? But then note that Q dot transpose is simply Q dot Q transpose the whole transpose. Okay? Which implies that, well, what does it imply? What does it imply for Q dot Q transpose? Right, think about it for a second. So you have Q dot Q transpose plus Q dot Q transpose, the whole transpose equals 0. What this implies is, I'll write it out in detail here, Q dot Q transpose is equal to the negative of its own transpose, right? Which implies that it is skew symmetric. For convenience, we are going to label this product omega. Okay, it's a skew-symmetric tensor, right? And out here we have, sorry, I need to have the transpose there. Okay, and on the right-hand side we have minus omega transpose. Okay, so what this implies for us now is that for rigid motion, the Eulerian velocity or the spatial velocity can be written as c dot plus omega x minus c, where omega is skew-symmetric, right? Where omega equals minus omega transpose. Okay? Now, here's another property of skew-symmetric tensors. It emerges that for any omega such that, ST means such that, right? For any omega such that omega equals minus omega transpose, one can also write out the tensor omega in the following fashion. It's skew-symmetric, so of course its diagonal, as we saw a few segments ago, has to be filled with zeros. We can write it out in this fashion. We're going to write it out as omega hat 3, omega hat 2, minus omega hat 1, and it's skew-symmetric, right? So here we must have omega hat 3 minus omega hat 2, omega hat 1. Okay? I've just chosen to write it this way, and I'm free to do this. Okay? Because it satisfies all the properties of being skew-symmetric. We've not introduced any new properties in doing so. But here's the rub. A skew-symmetric tensor omega acting on any vector, and in particular x minus c, is simply equal to the omega hat vector cross x minus c, where omega hat is simply omega hat I EI. Okay? There is this way of rewriting the product or the action of a skew-symmetric tensor upon any vector. Okay? And this holds for all x minus c belonging to R3. Okay? It doesn't matter that we had x minus c in particular in this expression. It could be any other vector. Okay? This always holds for any skew-symmetric tensor omega and any vector on which it acts. We can rewrite that product as the result of a vector omega hat crossed with x minus c. Okay? This symbol, of course, is for all, right? This means for all. Okay? So, we put all of this together, and what do we get? We see that for rigid motion, the Eulerian or the spatial velocity is this quantity, c dot, which is just the velocity arising out of the translation, right? Plus omega hat, the vector, crossed with x minus c. Okay?